So this integral is not challenging. We could punch that out pretty quickly, and we get u of bending is p squared L cubed over 6EI. That is not the deflection, that is the strain energy, okay? To obtain the vertical deflection, we actually have to equate the external work to the internal strain energy. As before, this is an energy method. And what is the external work? That's pretty quick to find too, since the P is at the point of investigation in the direction of investigation. The work here, again, it's a slowly rising P, so the work should be, hit the pause button. Yes, the work should be 1/2 P times V tip, and that's equal to the strain energy, and we get V tip is PL cubed over 3EI, your famous stiffness for a cantilever, 3EI over L cubed. So, there's something funny though. I hope that you noticed this, or maybe you didn't notice it, but I'm going to point it out to you right now. This is the strain energy for bending, and this is V tip. And they look like they have something linking them, which is pretty ding-dong obvious, and it's right here at the bottom of this page. The partial derivative of this strain energy with respect to P looks suspiciously like the answer. So what's going on here? Well, I didn't figure that out. Antonio Castigliani figured that out in 1874, and it's Castigliano's theorem. So it's a very beautiful idea. It links over several courses. So let's take a look at it in some detail. We start with our potato. It's constrained, so it's stable. We got a whole bunch of loads on it. But I have point I here, which was originally at the tip of the potato, and after all of the loads are applied, point I ends up somewhere else. So I got a zoomed in detail over here. But all of these methods that we've discussed only link the forces to the deflections, the deflections to the forces in the direction of the force. So it has to be parallel to PI. It's got to look like that. That's the delta that we're getting, not this. So what's going on here? So as I said here, the body is deformed by all of the loads. We are interested in finding delta I, which is the component of the direction. So let's take a look at this here. U is the strain energy when all of the loads are applied. So we have all of the loads are applied. The regular loads are applied. Then we put on a dpi, so it just wiggles a little bit. And now when I mean wiggle, it doesn't geometrically wiggle, but this load wiggles a little bit. The ith load wiggles a little bit in this direction. In this direction. It varies, it's perturbed a little bit here. So the change in strain energy is partial U partial I times dpi. So the way I explain it here is this is the rate of change of U with respect to pi, and this is my increment, dpi. All right, now the next thing is a little bit subtle. Suppose I put the pi on first, the dpi, the little increment of pi, that goes on first, and then all of the loads hit it, but dpi doesn't change. So dpi goes for a ride. We've seen this many times already. So what's the external work here? First of all, the dpi is slowly rising, so it's the triangle, 1/2 dpi times this ddi, and then the dpi load goes for a ride di. So it's a rectangle, it's not a triangle.